The field, acceleration, velocity, position physics stack. Important subatomic distances. By Arno Weigen, 2021. This is an introduction to a simpler physics that operates by splitting Newton's third law, acceleration equals force divided by mass, into underlying equations, so we only have acceleration equations in the normal physics stack. The field, acceleration.
The subatomic world is the combination of many base concepts. These cover A. Fields and distances, B. 3D mechanics and the related math of integrals and derivatives, and C. Statistical mechanics, also called quantum mechanics. These are interrelated, so those concepts are highly interlinked. Thereby, you will need to interlink those fields with their 3D mechanics and eventually understand now and why that creates statistical mechanics. This session will explore and relate the most basic set. If you need more on any of the underlying concepts, there is a separate session on each. Today, I will link the interactions types to the hemispherical coordinate system to my Bose two cylinders from the static 3 vectors of those interaction types. The subatomic world is the combination of many base concepts. From those concept groups, I will discuss specific times today. Within the interaction type set of concepts, we will use radial electrostatic, radial nucleostatic, also known as strong nuclear, axial nucleostatic, also known as weak nuclear, and that radial nucleostatic will act as the extra 1/r to keep electrons in shells, although without the current wrong Bohr naming of the concept as orbital or as angular momentum. Within the distance set of concepts, we will use the speed of light, the particle edge, the equilibrium radius of Bohr for hydrogen, then the further average settling position distance of larger atoms, and the scaling factor ratio of that equilibrium versus edge, previously called the fine structure constant. Finally, we will explore the strength and the related current mixed constant set of concepts. Planck's constant, of course, electrostatic charge, and mass, the most difficult concept in subatomic physics. From those concept groups,
The first, and most powerful, field distance is at the particle edge. Physics uses the symbol R sub e. All fields build to their maximum at the particle edge. That is simple enough. Yet, as you can see from the graphic at the right, with the particle force at the center, and the wave field at the two poles. That means we have three behaviors. How the whole operates, and then how each poles will operate, which might be different. Remember that there are two types of fields, but three operating positions. The radial, isotropic field operates as if the whole particle. This can use the point equations. These forces cause the particle in duality. Those include radial electrostatic, with symbol R, capital ES, and radial nucleostatic, with symbol R, capital NS, which I think relates to the strong nuclear force. That nuclear is why I call it nucleostatic. That leaves the weak nuclear force, my axial nucleostatic field, which is towards the axis. To me, that have the math of Dirac monopoles, but with duopoles. Those act as if two fields spaced at the particle edge. Further, as the system rotates, the axial nucleostatic causes wave functions. So, all particles have radial, particle fields and axial, wave function fields. Duality is just like people have height and weight, both are inherent, but the two are different measurements. For example, a moving particle by particle forces would move in a straight line, but because the axial field rotates with that tiny at the edge orientation, that give a tiny wobble. Again, two different fields cause those strange and amazing subatomic particle behavior. Remember that most equations need to calculate from this maximum field strength. For example, for electrostatic that strength is the charge. All the equation is understand that protons are positive that strength, and electrons are negative that strength. However, the whole picture is more complex, so let's review the other distances. There is a system to like them all. The first, The second critical distance in subatomic physics is the Bohr radius for hydrogen, symbol A sub 0. That is the spacing for the simplest interaction, one proton, one electron. It is the distance, beyond the particle edge, where the radial accelerations come in balance. The graphic at the right explains the equilibrium. This is the radial balancing that keeps electrons in shells, fields, at equilibrium distance, Bohr for hydrogen. Please remember this is A, distance from the nucleus on the x-axis, and B, physics strength on the y-axis. The math is physics positive is repulsive, that is, the objects accelerate away from each other, increasing distance, or really relative velocity. Hence, the positive for increases. That means that physics negative is attraction. The objects accelerate towards each other. The velocity relative to each other decreases. Please remember that. The red line is the radial electrostatic field and its acceleration, which for acceleration decreases at 1 over distance squared. It goes to physics negative infinity. It is increasingly attractive for electron to proton interactions. Opposites attract for electrostatic. That if alone is the electrons fall into the nucleus. Dilemma. Yet, electrons stay in shells because of a counterforce with an extra 1 over r. Now, Bohr wrongly assigned causation as a gravitational orbit, so the name, even today, is quote, orbital, unquote, quote, angular momentum, unquote. The Bohr name is wrong, the Bohr causation is wrong. But, the math is correct. The blue line is that radial nucleostatic field and its acceleration, which for acceleration decreases at 1 over distance cubed. Exponentially greater change than electrostatic. The basic math is that 1 over distance cubed decreases faster. That is why it is called a nuclear interaction. Its strength is huge at the nucleus, but immaterial at any distance beyond 10x the atomic shell. Think about it, 1 over 10 cubed is 1/1000th, so it become tiny and immaterial. As a result, scientists, including Bohr, ignored it. This radial nucleostatic field I associate with the strong nuclear force. The green line is the combination. That nets to zero at the Bohr radius, the electron spacing equilibrium. Remember that charge at particle edge was 352 million greater than Planck hc. This nucleostatic field at the particle edge is 6.51 trillion times stronger. Not billion, but trillion. That is the fun, amazing math of exponents. While 1 over distance cubed become immaterial at beyond atomic distances. At nuclear, the edge, distance 1 over distance cubed is exponentially larger than electrostatic. That becomes a wall of repulsion. Electrons by electrostatic fall into the nucleus until they hit that inelastic wall at the Bohr radius. The 1 over distance cubed quickly overwhelms electrostatic. The atomic model gets the graphic at the right of the simplest 1 proton, 1 electron. The second
These two main types of radial interactions are different in their exponent, 1 over distance squared versus 1 over distance cubed. But also the two are different in which particles interact. Those interaction tables are at the right. Please note that I have color-coded those so the red is repulsive, that is physics positive, and the green is attractive, physics negative. Those match the math direction of the acceleration caused. First, we all know the electrostatic rule, opposites attract and like-kind repel. However, most people do not know that comes from the math product. That a negative times a negative is a positive, and the positive times a positive is a positive, but the negative times a positive is negative. As such, you get the grid at the right. Also note that with a product, the zeros, that is the neutrons, have no interaction as the product times 0 is always 0. The particles are identified by this electrostatic attribute as either positive, a proton, negative, an electron, or 0 for a neutron. These are called the charge properties. However, there is another set of properties, the mass properties, which also have an interaction mapping. Number 1. In field acceleration, that mass properties is different than textbooks of the last century. Here, the mass interactions are where any one particle has a physics color. The second table at the right explains the complete set of interactions. Number 2. Further, you only need one particle with mass, so electron-nucleon generates nucleostatic force, when the textbook only teaches strong nuclear force between protons and neutrons in the nucleus. The textbook says that the strong force is between physics color particles. However, field acceleration uses any color particle as causation, not requiring both. Number 3. This direction is always opposite of electrostatic. The green two corners in electrostatic are red repulsive and nucleostatic. Number 4. Finally, nucleostatic interactions are based upon type variance. That is, the same type do not express. The fields do not interfere. One can see that by the diagonal 0 results when the particle types are the same in the interactions. Number 5. This is most important because electron-electron interaction do not express nucleostatic. They only have the p to p electrostatic repulsion. That lack is probably why physics for centuries focused on equations in the electrostatic format. However, for particles with a change for A:B that activates the nucleostatic interaction. However, the standard charge signs work here, just differently. The combination still occurs, but with that number 3 reversal. As a result, electron-nucleon is repulsive, physics positive. That is green in the table. That is the physics model for electron shells. Yet, proton-neutron is attractive, physics positive. That is green in the table. That is the reason for multiple particle nucleus binding. In this way, charge and mass are not separate at different interactions types from the sign charge feature in each particle. These two
The ratio of those two distances will appear repeatedly as equations scale up the Planck-Bohr hc to the particle edge strength. Scientists found that ratio in the abstract and called it the fine structure constant, symbol alpha or alpha sub e. That is a distance over distance ratio. In that way, the fine structure has no units of measure. However, the scaling is those distances. So I always will use the distances, a sub 0 over r sub e. That ratio will apply at the appropriate exponent, 1 over n. That is math equations, like renormalization is really evaluation of the steps as they change in position, but always with the universal scale using those physical distances, a sub 0 over r sub e. Then at the appropriate exponent, n. My use of the ratio is critical as that gives the physical model. You know if the position in a field is changing from edge to equilibrium or equilibrium to edge. You see, in different equations, the static scaling factor will have one side or the other substituted with actual positions in the field. With my distance ratio, it is easier to substitute the correct one. With abstract fine structure constant, there is confusion which to use alpha or 1 over alpha. Further, the relative scale, important when I get to elementary particles, is radius versus a sub 0. Those derivative ratios from one or the other distance is because I substitute all abstract mixed constants with Planck, the speed of light, and the two critical distances. In that way, equations always conserve energy, conserve momentum, and have number of particle units. This is another critical guideline for the field, acceleration physics stack. Only physical constants. Eliminate abstract mixed constants. The ratio
There are generally two reasons for electrons in elements larger than hydrogen for the overall shell average to be greater. The first is that the nucleus has more neutrons, so that adds repulsion, without electrostatic attraction. The neutrons are repulsion, radial nucleostatic only. I won't address that here, but those neutrons cause electron shells to settle by those extra spheres of repulsion fields. The second reason is that Pauli pair electron at 180 degrees. It settles at the position farthest from the target electron, but still net attracted. This is both electrostatic and nucleostatic, but that calculation can be simplified. The main variant is that the electron nucleon has nucleostatic strong repulsion, and that electron-electron Pauli hemisphere pairs does not. So, that is balancing the standard hydrogen, with the extra for nucleostatic, at 1 over distance cubed, but at 2x. Its position is over in the other hemisphere. So, that distance is 2x. But the strong, radial nucleostatic is a 1 over distance cubed acceleration. As such, Its strength is 1 over 2 cubed, which is 1 over 8. Compare that to the full for the nucleus at 1, and you get a net repulsion of 7/8 extra. Since I are trying to find the equilibrium, the natural positions would be change the distance by 1 over that, so 1 over 7 th8, and that means the two-cylinder distance is 8/7 ths. 8/7 ths bore A0. There are
These various distances occur throughout physics. Please remember that the variances are based upon that equilibrium versus edge scaling factor, the fine structure constant, alpha. That ratio is 18,778. As a result, I will use the logarithmic scale for this presentation. As discussed, the most important distance is the equilibrium distance, the Bohr hydrogen radius, called A0. That is the distance where both radial electrostatic acceleration and radial nucleostatic acceleration balance. The gross strength of both are Planck's constant, specifically h-c version. I base every calculation on Planck at Bohr. I do think of Planck's strength as separate. It is the acceleration strength at that distance with either field. That means that the gross strength is stronger closer to the nucleus. Specifically, at the particle edge, the strength is electrostatic charge. Planck at Bohr is increased by the equilibrium versus edge scaling factor squared for electrostatic to get the standard, gross particle charge. However, mass is also larger closer. That is overlaying the extra above that electrostatic charge is the variable mass. Mass is the extra of the 1 over distance to the fourth to move that electrostatic field. Please remember that radial electrostatic field is 1 over distance cubed at the field level. So, that means the scaling factor for mass is how much electrostatic to get the nucleostatic static. That means from the third power to the fourth power. That means the scale of mass is the power of 3/4. That is the main particle edge, that is the mass of the proton in the overall system center. So, both the variable mass of a proton and the electrostatic charge both are defined based upon the position in a field at the particle edge. That makes sense, particle's full strength is at the particle edge, and the field scaling starts from there. However, the last distance is the standard two-cylinder for electron shells. That distance I calculate at 8/7 times Bohr, then times the extra for the anomalous moment. That is the distance in the overall atomic system for reference for electrons. As such, that is the electron mass. That electron mass is less than the proton variable mass. That lower electron variable mass is that exponent of 3/4. Further, that lower electron variable mass gets reduced by the distance of 8/7 A0 times 1 plus the anomalous moment to the 3/2 power. That 3/2 comes from converting form electrostatic acceleration at 1 over 2 power to radial electrostatic 1 over 3 power. As such, the electron acceleration has less field resistance because those electrons are further out in the field. These distances, as positions in fields, are well established, but they are also the basis of the critical subatomic physics equations. Further, before me, there were separate, mixed constants, A, not all related to Planck, and B, not all related to settling positions in the fundamental fields. Specifically, at the particle edge, the strength is electrostatic charge. Planck at Bohr is increased by the equilibrium versus edge scaling factor squared for electrostatic to get the standard, gross particle charge. The graphic shows the electrostatic strength as the blue line. It shows the nucleostatic as the orange line. That is stronger inside Bohr, but weaker outside Bohr. There is also nucleostatic alone, which is a neutron, that is the gray line, and slightly less than just nucleostatic.